Hello everyone, my name is Erfan Oliaei. I'm a PhD student at KTH and Rice Research Institutes of Sweden. I'm really happy to be at international webinar on polymers, plastics and composites. Here's the topic of my presentation, microfibrillated lignocellulose from unbleached Kraft softwood pulp. And at first I will give you a short background and I will talk about how I have prepared Kraft pulp fibers and MFLC from them, and talk about morphology of my MFLC, on the characterization of MFLC films, and then I shortly conclude. The story of MFLC goes back to early 1980s, where for the first time Albin Turbach and his co-workers have been trying to homogenize water suspension of bleached pulp fibers with very low amount of lignin, and after several rounds of high pressure homogenization they got a gel-like whitish material, and they called that MFC, or microfibrillated cellulose. Since then, most of the research in this area was focused on bleached samples with low amount of lignin. For the first time, Kentaro Abe and his co-workers at the University of Kyoto 2009, they have tried grinding of CTMP with high amount of lignin, and then they got microfibrillated lignocellulose with quite high residual amount of lignin, and then they did vacuum filtration on the MFLC suspension and did hot pressing to make these films, and they showed that these films are quite strong and promising. You can see in this picture that when we have lignin present, because of the characteristic of lignin, that this is rather brownish. I took spruce wood chips and did standard Kraft cooking. You can see the conditions here, but I took different samples at different cooking time, and then I got pulp fibers with different amount of lignin. I should say that to prepare pulp fibers with high amount of lignin and short cooking time, I had to do also mechanical defibration to separate fibers from the wood tissue after cooking. And to get pulp fibers with very low amount of lignin, I also did the lignification bleaching on the sample. You can see that the pulp fibers are called FK114 up to FK2. This is kappa number, the number which comes after K. And this is a measure of lignin content. You can see the class on lignin content here if you want to have a more clear look. And yes, I have measured the total charge density on the pulp fibers. You can see that the pulp fibers with higher kappa number linearly have higher charge. So there is a linear relationship here between charge and kappa number on the pulp fibers, and this charge may make it easier during the fibrillation because of electrostatic repulsion between fibrils, may help in the fibrillation process. But on the other hand, the lignin itself acts as a binder and it holds the fibrils together. So we have two different mechanisms. One is helping for the fibrillation when we have higher amount of lignin, but lignin itself is as you can see on the right picture, is holding the fibrils all together. So the hypothesis is that there should be a point, optimum amount of lignin, that because of high charge it is quite easy to release small fibrils, but still we have quite high amount of lignin. You can see pulp fibers in this upper pictures. Fibers with kappa 2, you can see some parts of them are collapsed and we can see kinks and curvatures on them. But when it comes to kappa 65 and kappa 114 fibers, you can see they are straight, they have less curvature and kinks. And here is the full chemical composition of the pulp fibers. You can see the pulp fibers with higher amount of lignin has lower amount of cellulose, but the hemicellulose content is quite the same for all pulp fibers. It's about 18 to 19%. And to prepare MFLC, I did PFI milling for 30,000 revolutions on the pulp fibers, and then dilute suspension of them were homogenized for 9 rounds to get the fibrils. It was the same procedure for all of MFLC, maybe different modeling. You can see the MFLC with kappa 2 in this picture. MFLC kappa 65 and 114. As you can see that still there are quite wide fibrils present, and they are sometimes branched, as you can see, and occasional entanglements occur also. The width of fibrils from kappa 2 is between 2.5 nanometer up to 800 nanometers, and it is the same for kappa 65, but MFLC with kappa 114 shows wider fibrils up to 2 micrometers, as you can see. So in the previous pictures, previous SEM pictures that I showed, it was not very obvious how small fibrils we can have. So to study very fine fibrils, I did centrifugation, and what comes to the supernatant is small fibrils. And I take care of the conditions of centrifugation because it's important to be below overlapping concentration to have right amount of time for centrifugation, and we should take care of centrifugal force as well. Okay, then we see very small fibrils for kappa 2, kappa 65, and kappa 114, as you can see here, and the frequency of and the width distribution in different samples, as you can see, is not very different, and the widths of fibrils are below 70 nanometers, below 100 nanometer, and we can call it nano-sized fibril. So if we separate the supernatant fraction and we dry this, so when we have the mass of supernatant fibrils into the whole, we can have nano-sized fraction or yield. Yeah, and when we calculate the nano-sized fraction yield, this plot occurs, and you can see that in the middle range kappa number the yield is higher, and I want to draw your attention to this special sample, kappa 65, because it has quite high amount of lignin and still it has quite high nano-sized yield. After that I have prepared films. You can see micropaper films when I had the whole fraction of MFLC and when I had just the supernatant small fibrils. I prepared the films with vacuum filtration and oven drying at 50 degrees overnight. You can see the optical transmittance and optical haze of the films. In here, solid lines are presenting the micropapers, and dashed lines are presenting nanopapers. You can see nanopapers have higher transmittance because they have smaller fibrils in the structure, and it's and they have less scattering sites, so they have higher transmittance. And in the films with higher copper number or higher lignin, we see that the transmittance is less. This is because of presence of chromophores in the lignin, and especially in the lower wavelengths, which is a characteristic of lignin to absorb light at lower wavelengths, blue light region, for instance. And here you see that the haze of nanopapers are quite high, is about 80%, and for the micropapers is much lower. So haze or cloudiness is much higher for the micropapers because we have larger and wider fibrils, and this is scattering sites which scatter light. Still, light is getting transmitted to a quite high extent, as we can see in the transmittance, but at larger angles, which makes them cloudy. Here you can see water contact angle on the micropapers with copper 2, copper 65, and 114. You can see for higher copper we have larger water contact angle, and it shows that this is because of lignin character, which makes high copper films less hydrophilic. And you can see apparent porosity, which is calculated back from density and the ultimate tensile strength modulus and strength of the films. You can see tensile curve of MP kappa 65 and MP kappa 2. They are almost as strong as each other, with ultimate strength about 230, 240, and their modulus is also quite the same, but for the micropaper with kappa 114, you can see that this is a little bit weaker. This is one reason is related to larger, to higher amount of porosity we have in this structure. And the nanopapers, you can see they are not stronger than the micropapers. One reason is that their porosity happen to be a little bit higher than the micropapers in the sample preparation. But when it comes to a nanopaper with kappa 114, you can see this is really weaker compared to the rest of samples. One reason could be related to higher amount of lignin present in this sample, not because of only higher kappa number, but it could be because of the lignin particles which get separated from the larger fibrils, but the larger fibrils themselves in the centrifugation sediment, but the lignin particles end up in the supernatant, even from the larger fibrils. So it should have more amount of lignin, which might compromise fibril-fibril bonding. So I said that MFLC with kappa 65 is really interesting because of high lignin content and high nano-sized yield. And I studied that further with fractionation to see what is the morphology of these fibrils, to study that better. So this fractionation setup was used before by or invented by Dr. Parlashon for fractionation of industrial MFC, and this is actually filtration through different metal sieves with different meshes. And I have prepared fraction 1, fraction 2, fraction 3, and fraction 4. You can see these fractions, or F, F1, F2, F3, F4 for the fibrils here, and you can see the widths of fibrils which retained under the on the meshes. And in fraction 1, you can see this is quite large fibrils with a really high width. And in this plot, you can see strength and modulus of micropaper with copper 65 from this work compared to literature data, the MFLC films. You can see that this is quite to the high side. This is related to high density and quality of the fibrils themselves and interaction between the fibrils. So by this, I would like to conclude that the Kraft pulp fibers with copper 65 combined quite high lignin content, about 11% lignin, with optimal yield of fibrillation, about 57% nano-sized fibrils, which is quite high compared to the rest of samples, as you can see here. And these pulp fibers with copper 65 actually yielded MFLC, which comprised about 96% of fibrils with the widths less than 0.8 micrometer. And the films from these MFLC, despite the wide range of microfibrils and large microfibrils, prepared films which are mechanically strong and comparable with the nano-sized fibril films from the literature. By this, I would like to finish and thank my supervisors, Professor Lars Bergeland, Tom Lindstrom, Dr. Fredrik Berthold, and my colleagues who helped me quite a lot, Pav Lindian, Hui Chen, Dr. Chung Wu, and the funding support of this work from SSF, Swedish Foundation for Strategic Research, STFI, Association of Interested Parties, and VVSC. And thank you all for your listening. And I'm really happy to take any questions.